Right, we're going to be doing algebra today. So yeah, this is the stuff we're going to be covering. Basically what a polynomial is, its properties, and then some cool stuff like Vieta's formula and the rational root theorem. So for polynomials, a polynomial is just basically an expression where you have like a bunch of variables to different powers added together. As you can see, so you have like x to the power of n plus x to the power of n minus 1, so on and so forth. So that's basically what a polynomial is. And then the numbers in front of the variables are what we call like coefficients. And then if p of I equals 0, then we call it a root of the polynomial. I'm assuming most people already knew that, so I'm just going to do this very fast. Okay, so uh, the highest power of the variable is what we call the degree of the polynomial. So for example, if the polynomial is just like x cubed plus 1, then we say the degree of the polynomial is 3 because the highest power is x to the 3. And then this leads on into the fundamental theorem of algebra, which basically states that a polynomial of degree n has exactly n roots, which could be like repeated roots. So for example, x minus 1 squared that has two roots, which are both 1, or they could be complex roots. You don't need to know what complex numbers are. So for example, p of x equals x to the 4 minus 16, because the degree of the polynomial is 4, it has exactly 4 roots, and you'll notice that 2 of them are real and 2 of them are complex. This is just some nice theory you need to know, I guess. And then, okay, so root form of a polynomial. So, you know when the roots of a polynomial are when like p of I equals 0. So every polynomial can be expressed in the form p of x equals any constant a multiplied by x minus the first root times x minus the second root times x minus the third root, etc. So if you notice, if you substitute x for r, any one of them, for example, like let's make x equal r1, then r1 minus r1 is 0, and then because like 0 multiplied by every number like becomes 0, that's why like p of r1 equals 0 basically. And then we can use this to solve for the roots of the polynomial. So we can take any polynomial, we can put it into the root form to find its roots. So for example, x squared plus 4x minus 5, you can put it into its root form, x minus 1 times x plus 5, which means either x equals 1 or x equals minus 5. It's some pretty basic content here. And then we have completing the square, which is basically when you, okay, I'm assuming, does everyone here know the identity a plus b squared equals a squared plus 2ab plus b squared? I'm assuming everybody knows that. That's basically what you're doing here. You just take, I think, normally a quadratic, and then you just turn it into a square form like that, basically. It's pretty basic stuff. You can do this exercise here. Find the minimum value of the polynomial p of x equals 2x squared plus 6x minus 3. Yeah,
Yeah,
give that a try.
the idea is doing it using completing the square. There are other methods, but I guess yeah, that's the point of the exercise. Okay, I'll go over how to do it. I mean, really, this should probably be more of an example than an exercise because we didn't actually really like say anything about how to complete the square. Um, so I think I'll go over the thing if Ethan would stop screen sharing. Okay, so what was it? It was like 2x squared. Okay, well, first of all, so I said we want to get into the form x plus b squared equals a squared x squared plus 2abx plus b squared. And right now we have 2x squared. Was it? I think it was plus 6x minus 3. Correct me if I'm wrong, but I think that was it. So the first thing we notice is, well, we got to pick an a, right? So we got to match up these two terms, a squared x squared and then 2x squared. So if we just directly match it up, we could get a is equal to root 2, but that's kind of ugly because it is a rational number. So what I'm gonna do a bit of a trick here to make the coefficient from the x squared a perfect square. I'm just gonna multiply both sides by 2. Okay, so now we have the first term in the form a squared x squared, and we can write it as 2x plus, and we still have to figure out b. So we go to the next one, 2ab, right? 2abx. We want to match it up with 12x. Well, 2 times a, our a here is 2, is 4. So 4 times b is 12. So we get that b must be equal to 3. And if we expand this, we get 4x squared plus 12x plus 9, which is looking pretty similar. These are looking pretty similar. It's just we need oh wait. So this should not be an equal this should not be an equal sign at the moment. It's just this is like we're still in the working stage right now. We need to shift this by constant. What this is actually equal to is, well, since it's plus 9, but we need to get to minus 6, we need to just minus 15. And then we see they're equal now. So actually we get that okay, realistically it should probably be something more like this. Is the correct way of working it. So when I say get in the form x plus b squared, that's a little misleading. You want Min to get exactly in the form x plus b squared. Jackie did message me, right? -3 is not of the form b squared. You get it of that form and then you shift it by some like constant term. What I mean by that is that like the x term is within the square, so the variable is inside this square, but you have a constant term outside of it. Okay, so we have 2 times p of x is equal to this. So we get p of x is and okay, the way we do it once we get to the stage, once we completed the square, we have our variable inside the square, is to find the minimum. The trick is basically that for any real x, a square is always going to be larger than or equal to 0, right? Like I mean, I think that's pretty intuitive, right? I mean, that's almost like the definition, right? A square is going to be larger than equal to 0. So the minimum of this value is going to be 0 because this square can't get smaller than 0. And so the minimum of p of x is just when this thing equals 0, and then you get 0 minus 15 over 2, which is -15 over 2. Another way you could have solved it, like without completing the square, is noticing that the vertex of the parabola. So, your parabola looks something like this. The vertex here, the x-coordinate is the average of the two roots, and you can solve for the two roots using the quadratic formula, then average them. Then you would get the x value, plug them to p of x, and you do get the minimum value there. So that's another way of doing it, but this way, I was just highlighting how to complete the square, I guess. So yeah, you want to get the first term into the form a squared x squared, and then work out the other stuff, and then shift it by the constant at the end to match your original polynomial. So yeah. Okay, we can probably move on now.
Okay, we're gonna move on to Vieta's formulas now. Now some actual new stuff. Okay, for Vieta's formula for quadratic. So if a quadratic is in the form ax squared plus bx plus c, what Vieta's formula tells us is that the sum of the two roots of the quadratic equals minus b over a, and the product of the two roots equals c over a. And this comes from the fact that the root form of the quadratic is equal to like ax squared plus bx plus c, as you can see from the bottom. So if you just expand that expression out and then just match the coefficients, you're going to get that thing up there. The two roots equals minus b over a, and then the product equals c over a. And this is quite useful because it allows us to connect the roots and coefficients of any polynomial. Well, not any polynomial, for quadratic specifically, but we can actually generalize Vieta's formula for any polynomial. This is a very intimidating formula, but yeah, I just get Chris to explain it with his tablet because I don't have a tablet.
Fair enough. Okay, I might go over just Vieta's formulas for the quadratics just a bit more in detail first. So if we have our general quadratic, it's good in root form, it will look something like this, right? Where R1 and R2 are our two roots. And if we expand this out, we get we also know this quadratic is of the form ax squared plus bx plus c, where this is just kind of like the expanded like way of like expressing the quadratic, right? So if we match up the coefficients, actually, so that should be all the way there. If we match up the coefficients of x squared, because the thing from the x squared should be the same, we see that, well, we see that a is equal to a. That's not very useful. Here we see that negative a r1 plus r2 is equal to b, and here we get a times r1 r2 is equal to c, and this gives r1 plus r2 is equal to negative b over a, and then this one gives r1 times r2 is equal to c over a. So that's quite useful. That I mean, like this gives us quite a good relationship between the roots. You can find the sum and the product only by looking at the expanded version of the quadratic, right? So if you had something like 3x squared. Actually, just let's go back to our previous example where we were trying to find the minimum of 2x squared plus 6x minus 3. And we said that the vertex here is the middle, like the x-coordinate is between the two roots, which is r1 plus r2 over 2. And we know that r1 plus r2 is negative b over a, where this term is a, this term is b. So we get that r1 plus r2 is negative 6 divided by 2, which is negative 3. And therefore, r1 plus r2 over 2 is equal to negative 3 over 2. So we know the minimum of this function actually actually occurs at -3/2. If you plug in -3/2 into this polynomial here, you should get -15/2, which was the minimum we found. Okay, so that's Vieta's formulas for quadratics, but it extends for any nth degree polynomials. And like for example, for a cubic, you could say you could write it in the form a times x minus r1 times x minus r2 times x minus r3, and compare the coefficients with ax cubed plus bx squared plus cx plus d. And what you'll notice is you would see that the sum of the roots is negative b over a. I don't know why I put an equal sign there. That's uh I don't know why I also put four roots there. I'm a bit stupid. And then if you take the product two at a time, so R1 times R2, R1 times R3, R2 times R3, those are the three ways of grouping um the two, like the roots two by like in pairs of two, and you sum them, you get that as C over A. And then there's only one way of grouping them in terms of like in groups of three, and then that gives you negative D over A. So what you should notice here is that it goes B, C, D, and it always starts with negative B over A, but then it switches signs every time. So negative B over A, C over A, negative D over A. And this pattern generally holds, right? I mean, you're probably not going to need this for like anything higher than like something like a cubic, maybe a quartic, right? Um, like I guess I'll write it for a quartic as well, and hopefully you should be able to just like generalize like the formulas, or like at least like know like what like kind of how they like what form they take. Um, so if this is your quartic with your coefficients A, B, C, D, E, then you should get that the sum of the four roots is, as always, it's always negative B over A. So when you take the sum of the roots one at a time, it's always going to be negative B over A. Then you take them two at a time, and there should be six terms in total here, because that is 4 choose 2. C over A, so you move on to the next coefficient divided by A and switch the sign. Then you take them in pairs of in groups of three, so there should be three of these in total. Then move to the next one, switch the sign. And then finally, if you multiply them all together, then you should get E over A. I think maybe the most useful takeaway is that the sum of the roots is always going to be negative B over A, where B is the coefficient of the second highest power. And the product of the roots is always going to be the constant over A, where it will be negative if it's a odd power, if there's an odd degree, and it'll be positive if it's an even degree. I think those two are the most useful ones. So obviously, you still got to keep in mind the other formulas. I think we're gonna do some examples with Vieta's formulas now.
Okay. Example one, if A, B are the roots of P of X equals 2x squared plus 7x minus 24, find the value of A squared plus B squared. Preferably using Vietas. I mean, you could just factorize it, find the roots, add it up, but like that's cringe.
Yeah. Sorry, it's not that hard to just not click anything. Should we go down to now? There is I think I'll just go over this one just as a, I'm like if you haven't done it yet, this will be a good like example. And then I think there's a harder one after this, which you can try yourself. We'll give you maybe a bit more time to try that one. So I'll just go through like the principle of how to do this. Okay, so okay, maybe I should have been paying a bit more attention. What Ethan, what was the polynomial? I do not remember, I'm not gonna lie.
Bro, it
I
was
was not good.
2x squared plus 7x minus 24.
Minus 24. Okay, so we have our polynomial here, right? A, B are the roots. And I think it was find a squared plus b squared. Okay, so we're going to use Vietas obviously to, to get some kind of like system of equations in terms of a and b. So since a and b are our two roots, we said that the sum of the roots is negative b over a. It's a bit confusing here since we're using a and b as the roots when earlier we were using them as the coefficients. But this one right here is b, and then this right here is a, right? Where the red b is different from the black b. So it's negative b over a, which is negative 7 over 2. And we have a times b is equal to c over a, which is negative 24 over 2, which is just negative 12. So we have our system of equations there. So we want to find a squared plus b squared. Okay, well, we got to get those squares in there somehow, right? So maybe we could just try squaring a plus b, right? And you get a squared plus 2ab plus b squared. But we don't want that random 2ab term in the middle, right? We don't want that. It's a good thing we also know the value of ab. So we can just do a plus b squared minus 2ab. And we know the value of a plus b. We know the value of ab. So this is negative 7 over 2 squared minus 2 times negative 12, which gives, I'm just going to use a calculator and cheat here. Okay, it gives 145 over 4, apparently. I don't know if I did any calculation mistakes anywhere. Maybe I did. Um, I don't think so. Yeah, yeah, that looks about right. So that's how to do this one. I think there'll be yeah. We have one more example with a cubic instead of a quadratic. Hope you guys remembered how to yeah those rules work for cubics.
Okay. Oh, it's blurry as hell. If P, Q, R are the roots of the polynomial x cubed minus x minus 1, compute P squared plus Q squared plus R squared.
But Ethan, do you want to unveil the other part of the question?
Wait, well, was this too easy or something?
Yeah, I just realized. I think this is a bit too easy. We gotta give him a bit of a challenge.
Oh my days.
Alternatively, we could just make it p cubed plus q
Ah, we're good.
p plus r cubed. Okay,
There
we
we
can
go.
unbox the second part of the problem that we covered up earlier because nah, nah. I'm not going through that. Just make a p cubed plus.
Yo, why not, bro? It's a great question.
No. I think p cubed plus q cubed plus r cubed is better.
Okay, fine. I'll cover it back up, bro. There we go.
Nothing happened there. Um, yeah, okay. I guess I think this like, if this is a bit too easy, you guys could try yeah compute p cubed plus q cubed plus r cubed as well. I'll go over both solutions afterwards. Okay, I'll give everyone one more minute before. Uh, yeah, one more minute, and we'll move on. Okay, that probably wasn't a minute, but I think I'll present the solution now. If Ethan wouldn't get off his damn phone and okay, so we had our cubic or degree 3 polynomial, x cubed minus x minus 1. And I'll just rewrite this to highlight the coefficients. So be very careful here. There's actually a 0 in front of the x squared. So the coefficient for x squared or the b term is 0, minus 1, and then minus 1. So here are our coefficients. So we can use Vieta to set up some equations now. Since p, q, and r are roots, we'll set them up like so. P plus q plus r, that's negative b over a, which is just 0. PQ plus PR plus QR is C over A, which is negative 1 over 1, or negative 1. And then finally, we have PQR is equal to um, D over, no, negative D over A. So it's negative 1 over 1, which is 1. Okay, so this is we have our 3 equations here. And what we're going to do is, well, we're just going to write out what we desire to find is, oh, sorry, p squared plus q squared plus r squared. Again, we can, first of all, just expand out p plus q plus r squared and see what we get. And if you expand this out, what you get is something like that. So since we don't want this, 2 times pq plus pr plus qr thing over here, we can just subtract that. Right? Which is nice for us because, again, we know the value of p plus q plus r, we know the value of pq plus pr plus qr. So this gives us 0 squared minus 2 times negative 1, which is 2. Okay, I might try squeeze this down a little bit just because running out of room here. Okay, so now let's try find p cubed plus q cubed plus r cubed. Well, we can kind of start off the same way, right? We do p plus q plus r. Oh, sorry, p plus q plus r. We cube that and see where that gets us. Well, that gets us our 3 terms, p cubed plus q cubed plus r cubed. But it gets us a bunch of unnecessary stuff as well. In particular, it gets us. No, I don't know off the top of my head what is p plus q plus r cubed.
I think it's plus
Wait,
3. Oh, never mind. You got it.
wait. P because p p r. So I think it's 3 times because that'll be 6, 18. 18 plus 3, 21. Yeah, so it should be 3 times. Okay, I don't know why I did it like that. Okay, if you expand this out, which is okay, admittedly kind of a little long. Okay, I think that is what you get. A good check is, I mean, on the right hand side you have three terms. On the left hand side you have three terms cubed, so you should have 27 terms on the right hand side. Which if we add them up, we get 18 plus 6 plus 3, which is 27. So this looks correct. Um, I guess that's nice. We see, at least one familiar face, right? We have PQR here, which we know, but we have a bunch of this stuff, which, P squared, Q, PQ squared. We don't actually know that. So we need to write that in terms of, in terms of oh shoot, I was not meant to round that. In terms of like the basic blocks that we have here. And so we need to write p squared q plus pq squared plus q squared r plus qr squared plus p squared r in terms of whatever the hell we had uh like in terms of pq plus pr plus qr, p plus q plus r, and pqr. Um and the way to do that is, yo, Ethan, got any ideas?
I think you multiply the first
Oh,
equation
that's
by the
so true.
second
That's so true. Okay.
equation.
What we noticed, right, is that if we multiply p plus q plus r by pq plus pr plus qr. Oh wait, you can just drag it down for more space. Oh shoot, it's because I was on vertical. Whoops. Okay, anyway. Um you get p squared q plus pq squared plus p squared r plus pr squared plus q squared r plus qr squared plus 3pqr. Okay, so we have, okay, this is a bit confusing, right? But we've gotten a p squared q plus pq squared plus p squared r plus pr squared plus q squared r plus qr squared in terms of things we know, because we know the value of that, we know the like numerical value of that, and we know the numerical value of that. So okay, this like this annoying thing here, right? I'm just gonna go ahead and be lazy and then call that like let's say capital A. So I can get rid of this and just write A plus 3pqr because I don't want to have to write that out. And then you notice that this here, if I get rid of all of that, that is just 3A. Okay, that's much tidier now. Okay, so let's work out what A is. Well, we know that P plus Q plus R, this is equal to 0. Okay, -1, and that's just 1. So, you get 0 is equal to A plus 3. So you get A is equal to -3. Okay, so we've worked out A is equal to -3. We can finally substitute that back into here. This 0 cubed is equal to p cubed plus q cubed plus r cubed plus 3 times -3 plus 6 times 1. And we get that p cubed plus q cubed plus r cubed is equal to is equal to 3 if you just rearrange everything. Wow, that took a long time. Okay, cool. So yeah, that was a bit of algebra there, but we stuck through. We made it through. We got p cubed plus q cubed plus r cubed is 3. Okay, that's great.
Okay. There's also another way to do it using this really whack formula. You know what I'm talking about? The AQ plus BQ plus CQ minus 3ABC formula.
Oh, that is one of the formulas of all time. Okay, that's not like this.
Do you want to go to that or not? Just keep going.
Actually, wait, but before, should I talk about something? Okay, I'll mention something, right? Like, okay, I know in the middle of that, it seemed like we were a bit lost, and it seemed like, like maybe it was a dead end, right? And almost it might have seemed like like we got lucky that it worked out that we were able to express it in terms of the things we already knew. But actually, there's a theorem. It's called like the fundamental theorem of like symmetric polynomials, and basically what it's saying is that no matter what like expression they give you, like p squared q plus p, if it's symmetric in 3 variables, which means if you like permute the 3 variables in any like of the 3 factorial ways and the expression stays the same. For example, pq plus qq plus r cubed is symmetric because no matter how you switch pq and r, the expression will stay the same. If it's symmetric like that, you'll always be able to express it in terms of the 3 like building blocks, right? The 3 like almost like elements: p plus q plus r, pq plus pr plus qr, and pqr. I think those are called the elementary symmetric polynomials of 3 variables. I don't know, something like that. But yeah, if they do give you a symmetric polynomial, you'll always be able to express it in terms of those quantities you already know from Vieta's formulas. So yeah.
Should I pull up the cool formula to show everyone?
No.
Okay.
If you want. Okay, I don't like.
Nah, that's all good. We'll move on. Rational root theorem. So the rational root theorem is basically just a theorem that helps you factorize large polynomials. So you're not gonna get a question where you just like they give you a polynomial and they ask you to factor it. So this is more like helping with intermediate steps of a problem because like you're not allowed to use a calculator in Olympiad math, right? So if you get a large polynomial, it's going to be quite difficult to factor it. And the rational root theorem can often help with that. So what it says is that let's say the polynomial has a rational root, which means it can be expressed as an integer divided by an integer. If it has a rational root in the form r over s, what it says is that the constant term of the polynomial, it's divisible by r, which is the numerator, and then the leading coefficient is always divisible by the numerator of the rational root. Do you want to talk more about this, Chris?
Sure. I'll just go with an example. Okay, while I prep this, can you just like randomly give me a cubic to factorize?
X cubed. Oh, nah, I
You
need to
make one
search
that
one
has
up, bro.
actual like solution.
I got you.
Well, like at least like rational solutions.
I got you, bro.
Okay, go on.
Hold on. God damn, let me pull up an expanding calculator real quick.
Okay, so I don't know yeah I don't know how to factorize this either, so you know I'm there with you.
You can work through it together. Okay, so we have 30x cubed minus 151x
No,
squared.
dude, what are you doing? What cubics are you doing? I'm not doing this, bro.
Fine,
A nice cubic. I thought you were gonna do
fine,
like x
fine, fine.
like x minus 2 times like x plus 3. Like what?
Sorry, bro, my bad. Like, what about? Oh, this is big as well, bro. God damn.
Mate, it's not that hard to just like expand like x minus 2 times x plus 3 times x minus a half or something. You know what I mean? Like,
Sorry, bro. Sorry. Oh, there's a coefficient of 69 in here. Is that all good with you?
what do you mean? And where are you getting these polynomials from? I thought you were expanding them yourself.
I am, bro. Let me.
It's
What
not
the
that hard to just do x minus 2
four?
times x plus 3 times 2x
Four.
minus 1.
I'll just do 6x cubed minus 35x squared plus 47x minus 12, bro.
Wait, what? 6x cubed minus 35x squared.
Plus 47x minus 12.
Okay, so imagine you get this cubic in an exam and you gotta factorize it. So the rational root theorem tells us that like any factor of this, or any rational factor of this at least, must divide, like if r is a root, then r divides 12 over 6. Is that the rational root theorem? I don't know, I wasn't paying attention. I hope that I hope that is. So we get that r divides 2. Is that? No.
Hey, do you know what you're talking about, bro?
I think this is all wrong. This is all wrong. This is all wrong.
Bro.
No, the rational root theorem, right? Wait, is it the numerator divides 12 and the denominator divides 6?
The numerator divides 6, and then the denominator divides. Oh, wait, I got it
What
wrong. It's
does
the
it?
numerator. Numerator divides
Yeah, okay.
12. My bad, bro. Okay, I didn't even know the theorem, bro. What's
This
so
is the most
whack?
irrelevant theorem. I don't care about this theorem. Okay, so we have a root. in terms of a over b, right? We have a divides 12 and then b divides 6. Did you give us nice numbers, by the way? Okay.
No, I got nice numbers, bro. It's nice numbers.
Okay, so time to start checking random crap. Okay, let's check x equals like 1, for example, right? So we have a is equal to 1, b is equal to 1. So we get x equals 1. Well, this is our root, right? So let's see, is 1 a root? Well, you plug in x equals 1, you get 6 minus 35 plus 47 minus 12. That does not seem like a root to me. No. That's unlucky. So then you try -1. I'm pretty sure -1 isn't a root either. I'm not about here saying calculate, so I'm just gonna cheat again and use a calculator. Hey, look, -1 is definitely not a root. So then you keep going. Let's try x. So like in particular, what I'm saying is that you're never gonna try something like x equals 7, because in that case 7 doesn't divide 12. So you know for a fact it's not gonna be like the root won't be 7, right? So the ones you want to check are like 1, 2, 3, 4, 6, 12. Then maybe like 1/2, 1/3. Okay, I don't know. This guy gave me a pretty hard cubic. There's quite a lot of things to check, right? But if the coefficient was something like x cubed and the constant term was something like 3, then the only ones you would need to check is 1, 3, -1, and then -3. Because you know for the fact that the denominator divides 1, so the denominator so it's an integer in that case, right? In our case, we have a bit more of a complicated cubic. Oh, why is r equal to a and b? Sorry, because we're trying to find a root. So r represents just a root that we're trying to find here, and we're saying it's a over b because we're looking for rational roots. Because the rational roots can help you find rational roots, which is numbers that can be expressed in the form a over b, right? So I'm saying that if r is a root of the form a over b, then we have that a divides 12 and then b would divide 6. Okay, so let's there's quite a few possibilities to go over here. So you like, I think in an actual Olympiad you wouldn't be getting cubics as random as this. It'll probably be a little easier. But if we try to factorize this, apparently they were nice. I mean, so there's at least one rational root here. We can keep going, right? Like for example, let's try to test the rational root 2, and you plug in x equals 2 and see if it works. Okay, and then it doesn't. So then you try 3. Okay, and then we're gonna pretend I tried a bunch of things until it worked. I'm definitely not going on my calculator to solve it right now. Because I'm not plugging in numbers here. Okay, so if I went to 4, I would have gone something that worked. Okay. So we tried 3, doesn't work. We tried 4, and 6 times 4 cubed minus 35 times 4 squared plus 47 times 4 minus 12. Hey, look, that's 0, right? So we know that x equals 4 is a solution. And once you get that once you get a solution, you know that you can. Okay, I don't know
Oh,
if you guys
by
know.
the way, that you stopped screen sharing.
Oh, I think it said something was wrong.
Oh,
Oh, okay. Well, anyway, you keep testing roots until you get one that works. Um, in this case, we get x equals 4 works. Do I want to switch it? Do you guys know how to do polynomial long division? Okay, well, I think that's beyond the scope of this course, this like thing anyway. So
do you want
oh,
me to just give you the roots, bro?
do we have anything else after this?
No, we're done after this.
We're done. Why don't we just go teach them like functional equations after this?
Now we can do inequalities, AMGM
Oh, we're doing
inequality.
inequalities next week. Because I mean, functional equations isn't even in the course. So,
Oh, that's gonna take a long time. We only have 5 minutes.
no, we can do substitution technique. Okay, fine. Whatever. Um,
We'll just pull up some questions from PST.
no, I guess I'll go over polynomial long division, right? Because that's kind of useful as well. Okay, so we know that. So we found earlier through trial and error that x equals 4 is a root. In particular, this means that the factor x minus 4 divides this thing, right? So we can do a bit of thing called polynomial long division. It's kind of like normal long division, but with like x's as variables. So, oh, sorry, you're confused why it equals 4. Oh, it equals 4 because okay, basically, I'll explain the way you use the rational root theorem, right? It doesn't really guarantee you an answer. It restricts the number of like things you have to check. So at the end of the day, you still have to check, right? But so if we're looking for a root of the form a over b, and there might not exist a root, right? But if like we're hoping we're like please let there be a rational root of the form a over b, then we know that a has to divide 12 and b has to divide 6. So I'll write the possibilities of what it could be, right? Like a could be one, like so we're gonna. Oh, sorry. It's not. Oh, sorry. This symbol here, I didn't explain it. This means A divides 12 and B divides 6. I'm not saying A is equal to 12 or B is equal to 6. This is yeah. Maybe I should have explained it here, but it's. So we have that A is either one of these, B is one of these, and then you can put like a negative sign in front as well. So you choose one of these from A. Let's say we choose like 2, and then for B we choose 3. So 2 over 3 is. Why doesn't it divide 12 and 6? That's the theorem, right? Wait. I mean, I could explain, I guess, why the rational root theorem works. Actually, I'm not sure I know. You can pull up PST, I guess.
Are you asking me to pull up PST?
Am I right? Is this the rational root theorem? I'm not like, talking out my ass, am I?
Yo, stop swearing, bro. Oh, cool, man. Yeah, it is right though. It is right.
That's right. I'm searching it up. I'm so paranoid right now.
No, it is right.
Okay,
It's just
like
it
the
is
theorem
right. It
basically
is
says,
right.
okay, look, I'll just explain the theorem real quick, right? It's that if you have a rational root, so you have it as a fraction, right? A over b, then the numerator of the fraction, I mean, if this is in simplest terms, by the way, right? So a and b, like you can't simplify anymore. Then a must divide the constant term, and b must divide the coefficient of the highest power. So a divides this term, and b divides this term. Um, I I don't think I remember the proof. I mean, it is in PST, but um, I think. Oh no, I think that what the proof is you. Should I go over the proof right now? It's you substitute an a over b, like you substitute an a over b into each of these x's, and then you multiply through by b cubed, and then you realize that yeah, you basically realize that a has to divide 12, b has to divide 6. So then instead of searching like because if you didn't have this theorem, you'd be searching random crap like you know does 3 over 7 work? Does negative 3 over 17 work? But here we know that there's only a finite number of cases we have to check before we find a rational root, which is like this is assuming that there is a rational root, but like I mean like if you should be able to factorize the polynomial, then there should be a rational root. Otherwise, it's like kind of impossible to actually like solve the question. And notice that sometimes, like not all of these are gonna give us unique like for example, if I pick a is equal to 1 and b is equal to 1, I get r is equal to 1. But if I pick a is equal to 2 and b is equal to 2, I still get 1. So it's not like picking one from a and picking one from b will give us a unique like value of r, but it's just that every value of r can be made by choosing one from a and one from b. So what I was doing was I was setting a is equal to 1, b is equal to 1, so I was checking r is equal to 1, and I checked r is equal to negative 1, and I checked r is equal to 2, and I checked none of those worked, and then I got mad, so then I went on my calculator and found that r is equal to 4 is the solution. But if you didn't have a calculator, what you would do is you would check 3, and then you would check 4, and then you'd be very happy that you found a solution. And what you would do then is you would say, okay, well, x minus 4 is a factor. So you can factor it out using. Do you guys know polynomial long division? Do you guys know how to do it? No? Okay. So what we want to do is we want to get rid of the 6x cubed term. So we want to multiply this x by something to get rid of the 6x cubed term. And well, it's pretty natural that you're going to multiply by 6x squared. So that's going to be the first thing that I put in my I don't know what this is called. quotient. What's a quotient? Is this a quotient? I don't know, right? But so I'm gonna line up with my 6x squared here just to keep everything neat. I multiply 6x squared by x minus 4 and see what happens. Well, that's 6x cubed, and here I'll get okay. So now I minus this 6x cubed minus 6x cubed, that's gonna be 0. 35x squared minus 24x squared is, well, it's 35x squared plus 24x squared, which should be negative 11x squared. I mean, I don't really need to 0 here. And I bring down the 47 plus 47x. So now I need to get rid of this negative 11x squared term. I'm going to do that again using this x. So I need to multiply this x by negative 11x to get rid of this. Negative 11x squared. And then, because I'm multiplying x minus 4 by negative 11x, this negative 4 is also going to multiply it and give us plus 44x. And then that's going to give us 3x as the remainder here, minus 12. And then I think it's pretty clear from here. You just do minus 3, and then the minus 3 and the x minus 4 multiply to give negative. What did I do wrong?
Yo, it's plus 3, I think, not minus 3.
Whoops. Yeah, okay, minus. Whoopsies. Okay, and then you get a remainder of 0 here, right? If x minus 4 wasn't a factor and you tried doing this, you would get some like constant term left over here. But because we know that x minus 4 is already a factor, we should get a remainder of 0 here. So we have successfully factored this thing as x minus 4 times 6x squared minus 11x plus 3. And then obviously you could just use quadratic formula here to get your other 2 roots, and then you've found all 3 roots. Okay. Oh, and then that's time. That's 9 p.m. Wow.
There is a little bit more on the rational root theorem in the handout we sent out if you want to look further, I guess. But like, basically, if you get a question that makes you factor a big polynomial, it's a terrible question. That's basically the general rule of thumb.
Yeah, just walk out the exam room. Not worth doing it anymore, to be honest.
Yeah.
Bad quality Olympiad, yeah, for real. Okay, is that all?
Yeah, I think that's all.
Not gonna go over functional equations.
No, the lecture on Saturday will be a good lecture because like inequalities is banging.
Yeah, make sure to come down. That would be useful.
That like inequalities is good, guys. You should come on Saturday.
This lesson, most useless lesson I've ever. Waste of everyone's time here.
Yo, bro, we're recording this, bro. They're gonna watch this and see we're dissing them.
I'll cut this out before I say no.
What?
Wait.
Nah.
Wait. Let me end the recording before I talk more smack.
Yo, nah.